Do you ever get this bathtub ring thing happening when you take a bath? It's this like scummy stuff, right? It's a little different than the hard water deposits that show up on the faucet, but this is like kind of slimy stuff. And if you're really disciplined and you scrub it off every time you take a bath, then it's not such a big deal, but who has time for that? This is caused by calcium and magnesium ions dissolved in the water. Tap water, especially around here, is considered hard. Hard water, it's got a lot of dissolved ions in it. So those react with soap molecules and form, it's described as a gray curd. Gray curd. And that's what makes, there aren't that many intersections. You only have to sound your horn at an intersection. Thank you. They did that yesterday too, multiple times, several trains in a row. Forms a bathtub ring. This can also be a problem when you're washing your clothes. Your whites can get gray because the magnesium and the calcium ions in the water react with the soap in the detergent and leave this bathtub ring basically on your white t-shirt. So one thing you can do about that is you can get rid of the calcium and the magnesium ions. You could put in a water softening system, or what they do with the laundry detergent is they put sodium carbonate in the laundry detergent. Sodium carbonate is soluble, sodium compounds are soluble. And when the sodium carbonate dissolves, you get carbonate ions, but when the carbonate ions run into calcium ions or magnesium ions, they form insoluble compounds, magnesium carbonate and calcium carbonate, and they will precipitate out of solution. That helps to prevent the calcium and magnesium ions from making this gray curd on your clothing. Around here, my experience is that the water is hard enough that the sodium carbonate in the laundry detergent doesn't help very much. So I quit wearing white t-shirts and I wear black t-shirts, and then you can't tell. Precipitation reactions are reactions in which you get a precipitate formed when you mix two solutions. So you have two aqueous solutions, they look like water, you mix them together and something appears out of nowhere. It's not magic, although it can seem magical. Here we've got, this looks like water, and we mix it with this stuff that looks like water, and we get this bright yellow stuff. And if we wait, that will settle to the bottom and look like a layer of, I guess, yellow snow on the bottom. You don't want to eat this, and you don't want to eat yellow snow. I grew up in Minnesota. I know about these things. So the solid that's formed is called a precipitate. It's an insoluble ionic compound. So here we've got potassium iodide. Is potassium iodide soluble? Yeah, potassium compounds are soluble. So here it's dissolved in water, it's aqueous. Here we have lead 2 nitrate. Nitrate compounds are soluble. This is aqueous. When we mix these together though, lead 2 and iodide together form an insoluble compound. And so that precipitates, it forms a solid, so we have S as our state symbol here, and that's going to precipitate. In meteorology, they talk about precipitation, you know, it's snowing in the mountains. There's snow coming down. When precipitates form, they remind me of snow. The solid forming and falling to the bottom. We're going to learn how to predict the products of precipitation reactions. So we do this by looking at the original ions. Here we have potassium and iodide and lead and nitrate. And something's happening that's different, right? Because there wasn't a solid here, there wasn't a solid there. So they must be switching partners. So the two possibilities are potassium with nitrate and lead with iodide. Opposites attract. These are positive ions, It actually bothers me a little that they don't have the charges on there. Plus, minus, minus, 2 plus. The lead and the potassium are not going to pair up and make an insoluble compound. 2 positively charged ions are going to repel each other. So the possibilities are potassium with nitrate or lead with iodide. And so we look at the 2 possibilities and we apply solubility rules, and we can tell that this one is soluble, so that would be aqueous. This one is insoluble, it forms a solid. And that's how we predict what the product is. So I have this imaginary place I call Mrs. K's Chemistry Land. Disneyland's the happiest place on earth. I'm pretty happy in Chemistry Land, but some students maybe aren't. But maybe it's happier than here. I don't know. So in Chemistry Land, this is like a party. And so I've told you before that I think of metals as being masculine and nonmetals as being feminine. So this is a guy and a girl, and they're going to go to this party. And here's another guy, lead and nitrate, his girl, and they're going to the party. And these guys are friends, but they're just friends, right? So they go to the party and everybody's mixing and mingling together, and potassium sees nitrate. I'm like, oh, hi, right? And then lead sees iodide, and he is just blown away. He's just so attracted to her, right? And they're not mingling anymore. They're like together, and they maybe found a couch or something on the back porch, and they're necking, and nobody else seems to know where they've gone. There was a chemical reaction. Okay? They have chemistry. So they precipitate. They're not in this party anymore. But potassium and nitrate are still here, but they haven't really changed. They were swimming around here, and they're still swimming around over here. They didn't undergo a chemical reaction, but lead and iodide did. That make sense? So, every time you mix 2 aqueous solutions, you do not get a precipitate. If we mix potassium iodide with sodium chloride, we bring this guy and girl and this guy and girl, and we put them together in this party, and they're mixing and mingling, and there's no chemistry. We're like, oh, hi. They're having fun at the party, but they're just mixing, and nobody goes off and makes out in the back room. No reaction. Because when we look at these two compounds, right, and we try to identify, okay, well, what could happen here? Here I've got potassium, and I'll use the same way that they did it on the previous slide. Potassium and iodide and sodium and chloride. And so we could get these 2 pairings, right? They're switching partners, essentially. So we look at potassium with chloride and sodium with iodide, and we look at in our heads, we look at the solubility rules. Are either of those insoluble? No. There's no reaction that occurs. There's no chemical change. There is a physical change because these were not mixed together before, and now they're mixed together. But it's a physical change, it's not a chemical change. Any questions?